For billions of years, the universe expanded silently in the absolute darkness of space, carrying within its structure the marks of its own birth. Every star, every galaxy, and every particle of matter is part of a story that began long before Earth existed. But there is a question that continues to echo among scientists, philosophers, and curious minds around the world. How old is the universe? The most widely accepted answer today is astonishing: approximately 13.8 billion years, a number so vast that it challenges human imagination. If we compressed the entire history of the universe into a single year, humanity would appear only in the final seconds of December 31st. This number, however, did not arise from assumption or belief. It is the result of extremely precise measurements, sophisticated mathematical calculations, and observations made with instruments capable of seeing almost back to the beginning of time. To understand how we arrived at this estimate, we need to return to the earliest moment we can observe. About 380,000 years after the Big Bang, the universe cooled enough for light to travel freely through space. Before that, everything was a dense and opaque plasma. When light finally escaped, it left behind a record. That record still exists. It is called the cosmic microwave background radiation, discovered accidentally in 1965 by Arno Penzias and Robert Wilson. This radiation is considered the thermal echo of the birth of the universe. It is the oldest light we can detect. By mapping tiny variations in this radiation, scientists discovered something extraordinary. These small fluctuations reveal information about the density, temperature, and composition of the early universe. Space missions, such as the WMAP satellite and later the Planck satellite, measured these variations with remarkable precision. The collected data made it possible to calculate fundamental parameters of modern cosmology. Among these parameters is the expansion rate of the universe. In the 1920s, the astronomer Edwin Hubble made a revolutionary discovery. By observing distant galaxies, he realized that they were moving away from Earth, and the farther away they were, the faster they receded. This meant something profound. The universe was not static, it was expanding. If galaxies are moving away from each other today, in the past they were closer together. By mathematically reversing this motion, we reach a moment when all matter and energy were concentrated in an extremely dense and hot state. That moment is what we call the Big Bang. By combining the measured expansion rate with information from the cosmic microwave background, scientists built a model called lambda CDM, currently the standard cosmological model. This model includes ordinary matter, dark matter, and dark energy. It describes how the universe evolved from its earliest instance to the present day. When this model is applied to observational data, the result converges to approximately 13.8 billion years. But the story does not end here. In recent years, an intriguing problem has emerged, known as the Hubble tension. When scientists measure the expansion rate using the cosmic microwave background, they obtain a specific value. However, when they measure this rate by observing relatively nearby supernova, the value found is slightly different. This difference may seem small, but its implications are enormous. If the current expansion rate is higher than the model predicts, the universe may be slightly younger than estimated, altering our cosmic timeline and requiring deep revisions of current calculations. If it is lower, the universe may be older than we imagine, meaning the first structures had more time to form and evolve than we currently believe. The discrepancy is not trivial. It directly challenges the internal consistency of the standard cosmological model and forces theoretical physicists to reconsider foundations that once seemed solid. Some researchers suggest that there may be a new form of energy or particle not yet discovered subtly, influencing the expansion of the universe. Others believe there may be small systematic errors in the measurements, perhaps related to instrument calibration or statistical interpretation of collected data. The James Webb Space Telescope has added new pieces to this puzzle by observing extremely ancient galaxies that appear more evolved than they should be for the currently estimated age of the universe. These observations have sparked intense debate within the scientific community, as they suggest that star and galaxy formation may have occurred more rapidly than models predicted. Did the universe form complex structures faster than we imagined, challenging our understanding of primordial physics? Or do our models require deeper adjustments, perhaps involving revisions in the physics of dark matter or the very dynamics of dark energy? Even in the face of these questions, the estimate of 13.8 billion years remains the most consistent with the current set of available observational evidence. It represents one of the most impressive achievements of modern science, connecting mathematical theory, astronomical observation, and advanced technology into a single number. Measuring the age of the universe is measuring the time of existence itself and understanding the true scale of the cosmos we inhabit. It means understanding when the first stars appeared, when galaxies began organizing, and how long it took for complex chemical elements to form inside massive stars. Without billions of years of stellar evolution, the carbon that makes up our bodies would not exist, nor the oxygen we breathe or the iron present in the core of our planet. Every atom in you was forged inside ancient stars that lived and died long before the birth of the sun, in spectacular explosions known as supernova. When we look at the night sky, we are looking into the deep past of the universe across different layers of time. The light from the nearest stars takes years to reach us, while light from extremely distant galaxies can take billions of years crossing cosmic space. This means that observing the universe is literally traveling through time, exploring eras that precede the very formation of the solar system. The farther we look with advanced telescopes, the closer we get to the first chapters of cosmic history. The age of the universe is not just a cold scientific number, but a measure that reshapes our perspective on reality and our place within it. If the universe is 13.8 billion years old, Earth, at 4.5 billion years, is relatively young in the broader cosmic scenario. Complex multicellular life emerged less than 1 billion years ago, showing that biology occupies only a small fraction of the total history of the cosmos. Human civilization, in turn, occupies only a microscopic instant in this immense timeline that stretches across billions of years. And yet, in just a few thousand years, we developed tools capable of measuring the age of the cosmos itself with astonishing precision. This achievement reveals something profound about the human mind and our capacity for mathematical abstraction and systematic investigation of nature. We are temporary creatures living in a vast and ancient universe, yet capable of understanding its history through science and reason. The question now is whether this understanding is complete, or whether we are only at the beginning of even more surprising discoveries. The Hubble tension continues to be investigated with increasingly precise instruments and refined statistical analyses. New space missions are being planned to measure cosmic distances with greater accuracy and reduce margins of error. If the discrepancy persists in the coming years, we may be facing a profound revolution in fundamental physics. Perhaps dark energy behaves differently than we imagine, varying over cosmic time. Perhaps there are invisible components not yet detected that subtly influence expansion. Or perhaps the standard cosmological model will need to be partially reformulated to accommodate new observations. Regardless of the final outcome, the search for the exact age of the universe will continue to drive future generations of scientists. Because understanding cosmic time is understanding our own place within this immense universal narrative. Each new measurement is an attempt to answer humanity's oldest question about origin and existence. Where did we come from, and how long has this story traveled to reach the present moment? The universe may be 13.8 billion years old, or perhaps a little more, or a little less. But one thing is certain. We are living in an extraordinary moment of cosmic history in which the universe itself can be measured by instruments created by an emerging species. A moment in which a species on a small planet has managed to measure the age of the universe and may be on the verge of discovering that there is still much more to learn about time, space, and reality itself.